So in order to see that you already know what a subsequence is, let's just think about your favorite divergent sequence, -1 to the end. So if you just start listing terms, you see that it's, well, I guess -1 to the 1 is -1, plus 1, -1, plus 1, -1, plus 1, and then it keeps on going forever like that. So if I were to ask you to find a subsequence of that sequence which converges, what subsequence would you choose? Well, if you grab like every other term, you'll get like a bunch of ones. So here's one. I mean, I haven't told you what a subsequence is, but this is all a subsequence means. How if you take just that sequence? Does that sequence converge? Yeah. So that's all a subsequence means. The formalism that's about to follow is just trying to capture that act of taking a subsequence and only studying every couple of terms in it. So our goal in doing things with subsequences is to ask the question, if I give you a sequence, can you find a subsequence that converges? Can you do that? Can you ignore a bunch of terms and eventually get something that does converge, even if your original sequence didn't? So let's formally define a subsequence. And the fact that you could kind of tell me that says you already have an idea what it means. So here's a definition. So let's let f from n to n be a strictly increasing function. So all that means is for every natural number n less than the natural number m, f of n is less than f of m. Let's let a be a sequence of real numbers. That is, a is a function from the natural numbers to the real numbers. That's all the sequence is. Then a composed with f. Well, that's another function from the natural numbers. F sends the naturals to the naturals. A sends the naturals to the real. So yeah, that's a function from the natural numbers to the real numbers. Is a subsequence of A. That's all the subsequences. And let's see if this gives a subsequence. So let's see, how did I select the terms that give just plus ones and -1 to the end? Which terms did I pick? That's an ambiguous, that's a weird question to ask. Yeah.
Just the even ones?
The even ones. So if you start with a sub n equals -1 to the n, if you only take even numbers, you get, well, what's a way of parameterizing the even numbers? It's things that are multiplied by 2. You get a sub. I'm going to use k just in order to follow the pattern that I'll use for subsequences from now on. Yeah, -1 to the 2k, that's always equal to 1. And let's just see if this actually makes sense. So is that the result of composing the function a with some other function? Is that other function strictly increasing? As k grows, does 2 times k also grow? Yeah. So just in order to keep track of notation, right, we usually write a sub n instead of a of n when we're talking about sequences. Similarly, instead of writing this thing down as a function, instead of writing down f of k, I'll write down n sub k. So the standard notation I'll use for subsequences will be something like a sub n sub k. Well, n sub 1 is less than n sub 2 is less than n sub 3 is less than n sub 4. So if you like, all this is just what it means to be strictly increasing. So that waxed a little bit technical, I think. what this is trying to capture is what it means to delete a bunch of terms from the sequence and take what's left over. So let's even just do some more examples. So let's think about the sequence a sub n equal -1 to the n and b sub n equal to 1 over n. Let's write down some explicit subsequences, and then we'll describe the limits of those subsequences. Do they exist? Do they not exist? Are they a particular number? So let's take a sub n to be -1 to the n, b sub n to be 1 over n. Maybe I'll fill in, like, I don't know, some entries at random, and we'll see what we can say about these. So if you take n sub k to be k, all right, that's not a very interesting subsequence. I'm going to get the exact same thing back, but with a different variable name. I'll get a sub n sub k to be -1 to the k. So tell me, as k goes to infinity, what can you tell me about the limit of -1 to the k? Doesn't have a limit. It diverges. And maybe just for the sake of variety, I'll hit that one, the one that we did. When n sub k is 2k, a sub n sub k is -1 to the 2k, but -1 to an even power is always 1. So a sub n sub k is always 1. What can you tell me about the limit of the sequence that is always 1? Convergence to 1. So by taking a subsequence, you can trick a divergent sequence sometimes into converging. Do you guys think you can fill out the rest of the entries in this table really quick? Also called b sub n or b sub n line. So you guys are like really quiet. What do you think? Should we just like talk through this now? When n sub k is k plus 1, what is a sub n sub k?
-1 to the k plus 1.
-1 to the k plus 1. Does that converge or diverge? Diverge. So I mean, it's like exactly the negative of what the original sequence is. Apparently for 2k it converges to 1. When you plug in n sub k equal to 2k plus 1, what is a sub n sub k? -1, which converges to -1. So, cool. This sequence has two different subsequences which converge to different things. When n sub k is k squared, tell me about the limiting behavior of a sub n sub k. Still diverges. Nice. What about b sub n sub k? When when n sub k is k, b sub n sub k is just 1 over k. What can you tell me about its limit? Converges to 0. What about when n sub k is k plus 1?
Converges to 0.
Still converges to 0. When n sub k is 2k, still converges to 0. All of the things that went in this column,
Yep.
they all converge to 0. Maybe I'll put the interesting stuff there. Converge to 0, converge to 0, converge to 0, all the way down. Now that last column, that's like the opposite of surprising, right? Like if you start with something that converges and you take a subsequence, as k gets big, n sub k gets big, but as n sub k gets big, b sub n sub k should get close to the limit of b. So if a sequence converges, then so should all of its subsequences. Here's today's first game. Let a sub n be any sequence, and a be a real number. Then a sub n converges to a. If and only if every subsequence of a sub n also converges to a. Let's prove it. Let's let a sub n be a sequence. So it's an if and only if, so there are like two directions. Let's do the one that seems to have like the stronger hypothesis. Let's assume that every subsequence converges to A, and conclude that the sequence itself converges to A. Let's assume that for every subsequence a sub n sub k of a sub n sub k converges to A. Now, in order to see the result, well, a sequence is a subsequence of itself, right? You can take the identity map to be the rule that gives you n sub k. So if n sub k is just k all the time, you get a sub n sub k is equal to a sub k. That's the same sequence as you started with, just with a different variable. So by assumption that converges, so the whole sequence converges. That argument makes sense? And that's like the obvious direction. Maybe it would be less obvious if you assume that like every proper subsequence converges or something silly like that. But who cares? Proof done. Let's prove the other direction. Let's suppose a sub n itself converges to a. And now let's consider any subsequence a sub n sub k. So one thing I'll say is, let's just make an observation with it. When you say let a sub n sub k be a subsequence of a sub n, you're really saying something about your choice of n sub k. You're only allowed to use a strictly increasing sequence. And there's a good reason for that. Let's think about, I mean, this is, there's a sequence. I guess it's the sequence b sub n equal to 1 over n. Should this be a subsequence? No, I've like fucked up the order. So a subsequence needs to have the elements, the terms in the same order as the original sequence. You're allowed to skip but never go back. Otherwise you can do something really dumb. So that's the point of this word strictly increasing. So let's put things together. I want to show that a sub n sub k converges to a. So that means I need to prove something involving an epsilon. So let's consider any epsilon bigger than 0. The only thing that I got to assume was that a sub n converges to a. Epsilon is positive and a sub n converges to a. What does the definition of the limit tell you? Being really quiet. What's the definition of the limit? Does it mean to say that a sub n converges to a?
The absolute value of a sub n minus a is less than epsilon for all little n greater than
I'll put it in the opposite order just to make the quantifier more obvious. What you said is correct. I can come up with a choice of big N, which is good. I need to come up with a choice of big N if I want to prove that A sub n sub k converges to A. The free variable in n sub k is now k and not n anymore. So instead I'll be assuming that like little k is bigger than something. Well, here's another important result about these strictly increasing sequences. If you have a strictly increasing sequence, then n sub k is always bigger than or equal to k. Which makes sense, right? If n sub k just keeps growing, it has to grow by at least 1 each time. So it should never be smaller than k. And the proof is really easy, it's just induction. So now let's see. So we consider any epsilon bigger than 0. We came up with a choice of big N. I should now assume that the free variable in A sub n sub k is bigger than big N. Let's suppose that little k is bigger than big N. But then n sub k is bigger than or equal to k, which then by assumption is bigger than big N. So if n sub k is bigger than big N, can I use the line that's, well, I guess the line that's above? I can, right? N sub k is bigger than big N. So, absolute value of A sub n sub k minus A is less than epsilon. By this. How do we feel? Everyone feel okay? Anyone have a point in this argument that they didn't follow? Any questions at all? Okay. So what have we done? We considered any epsilon bigger than 0 in this line. We came up with a choice of big N. We considered any little k bigger than big N and showed that A sub n sub k minus A is less than epsilon. So we just proved that A sub n sub k converges to A. But we did that for absolutely any subsequence, so that proves the result. How do people feel about that proof? People want to see the proof of the claim? Yeah, let's do it. So as I said, let's try induction. Maybe I should start with this. Let's let n sub k be a strictly increasing sequence of natural numbers. Because that's what the claim assumes. I need to prove that n sub k is bigger than or equal to k for every k. Let's proceed by induction on k. Base case k equals 1. I need to show that n sub k, let's switch colors, is bigger than or equal to 1. Why should that be true? Yeah.
N1 is in the natural numbers, and any natural number is greater than or equal to 1.
So why is this true? This is true because n1 is a natural number, and 1 is the smallest natural number. So n1 must be bigger than or equal to 1. Awesome. People feel pretty good about that? Let's do the inductive step. So pick some natural number k, and let's assume the result that we want to prove for every natural number, but only assume it for this particular natural number. Let's assume that n sub k is bigger than or equal to k. We must show n sub k plus 1 is bigger than or equal to k plus 1. All right. Let's just try to write down the facts we know. What do I know about n sub k plus 1?
It's greater than n sub k.
It's greater than n sub k. So let's I'll just gather together facts here. And we'll see if we can put these together. What else do I know?
K plus 1 is greater than K.
Mm-hmm. In fact, we know something a little bit better than this. We know something a little bit better. That K plus 1 is the least, maybe I'll say smallest. Cool. What else do we know? What's the inductive assumption?
N sub k is greater than or equal to k.
Good. So do you think, so how would you want to combine these facts to get the result that we want? Let's see, does it follow that n sub k plus 1 is strictly bigger than k? And k plus 1 is the smallest thing that's strictly bigger than k. So what can you conclude? So n sub k plus 1 needs to be bigger than or equal to the smallest thing that's bigger than k?
Or wouldn't it just be equal to it?
Oh, it might not be. Right, we've seen that like n sub k could be like 2k. So there might not be equality.
So then, since it's the smallest natural number, then n sub k plus 1 is greater than or equal to k plus 1.
Yeah. N sub k plus 1 satisfies the condition that it's bigger than k. So it's in the set of all things bigger than k. But k plus 1 is the smallest thing in the set of all things that are bigger than k. So you get an inequality. So let's write that down. Well, let's see. N sub k plus 1 is bigger than n sub k is bigger than or equal to k by 1. The assumption that n sub k is strictly increasing. And 2, the inductive assumption. So n sub k plus 1 is bigger than k. Now, k plus 1 is the smallest natural number greater than k. So, since n sub k plus 1 is bigger than k, we see n sub k plus 1 bigger than or equal to k plus 1. How do you feel about that? Does that seem okay? And that's a claim that we'll use with some frequency. This claim. So let's do some things using that theorem that we just proved. So you already know that negative 1 to the n diverges. We proved it, I guess, using like a proof by contradiction. We assumed there was a limit, and then we chose epsilon equal to 1 and got a contradiction. Let's try a different approach. Using that theorem, that will tell us that it doesn't have a limit. So let's suppose that negative 1 to the n converges. If it converges, then it has a limit. Let's let the limit be equal to L. Once you know something converges, you can give its limit a name. But let's use what we know. A sub 2k, what is a sub 2k if a sub n is negative 1 to the n? Well, it should be like, it's 1. Yeah, it'll be negative 1 to the power 2k, which is just 1. What's the limit of that sequence? 1. But by theorem 2.5.2, the theorem we just proved, what must the limit of a sub 2k be equal to? Assuming that a sub n converges to L. And limits are like well defined. So it must be that 1 is equal to L. Gesundheit. What's another subsequence that might be useful to get us a contradiction? So I guess this says that if the limit exists, the limit has to be 1. Do you think we prove that if the limit exists, it has to be negative 1? Yeah. What subsequence should we use? That's stupid. We should look at the odd entries. So if we let n sub k be 2k plus 1, then we get a sub 2k plus 1. Well, that's negative 1 to the 2k plus 1. Well, that's always negative 1, which converges to negative 1. So by that same theorem, negative 1 must be equal to L. So that means that negative 1 equals L equals 1. So negative 1 is equal to positive 1. Is that a contradiction? Yeah, it's like an obvious contradiction. Negative 1 is not equal to positive 1. One of them's negative. Cool. So, like I've been bandying this about, like negative 1 to the n diverges. But we're going to see that, well, it's not page 1. Negative 1 to the n diverges, but it has subsequences which do converge. And we use them, in fact, in that argument. The goal of this next couple lectures is to answer the question, what sequences have convergent subsequences? And I think we'll even make it to the statement of the theorem today. In order to kind of study this, notation isn't the right one. I'm going to reformulate what it means to be the limit of a sequence, limit of a subsequence. No, I think that's correct. That is what I want. I don't think I should cross that out. So I want to address the question of, does a sequence have a convergent subsequence? So let's kind of turn things around. If a sequence has a convergent subsequence, then I can talk about the limit of that convergent subsequence. That makes sense, right? If subsequence converges, it has a limit. You can talk about its limit. Here is a definition. So let's let A(n) be a sequence, and A be a real number. Then I'll call that number A a subsequential limit of A(n) if there is a subsequence of A(n) which converges to A. And that's like a super, like that's a well-stated definition, right? What it means is in its name. So, yeah, let's do that. So if I were to ask you, what are the subsequential limits of negative 1 to the n? What do you think they are? Can you tell me some subsequential limits of negative 1 to the n?
Negative 1 and 1.
Negative 1 and 1. Do you think there are any others? I'm not asking for a proof.
No.
Yeah, it doesn't seem reasonable, right? There shouldn't be any others. So here is an exercise which is in fact part of the homework for today. The set of all subsequential limits of negative 1 to the n. The set of all subsequential limits of negative 1 to the n is exactly the set containing 1 and -1. So let's go back to like the statement of goal. I want to say, when does a sequence have a convergent subsequence? Well, that's the same thing as saying that that sequence has a subsequential limit, isn't it? You could say, oh, well, if it has a subsequential limit, that subsequential limit is the limit of a subsequence. That subsequence is the convergent subsequence that we were looking for. So instead of trying to prove directly that a sequence has a convergent subsequence, I'll try to prove that a sequence has a subsequential limit. Or some proofs make that approach. So let's let A and B a sequence, and L be a number. The following are equivalent. The number L is a subsequential limit of A sub n, and for every epsilon bigger than 0, and every m, there exists a little n bigger than big N, which satisfies that the absolute value of A sub n minus L is less than epsilon. What do you think? Does that look an awful lot like just the definition of the limit? Maybe in order to appreciate how similar and at the same time how different it is, let's write down both of those in just the full formality. What's the definition of A sub n converges to L?
For all epsilon greater than 0, there exists an n such that when little n is bigger than n, the absolute value of n minus L is greater than epsilon. Or sorry, less than epsilon.
Yeah, right, less than 4. Let's write down that statement. Versus, for every epsilon bigger than 0, for every big M, there exists a little n bigger than big M, such that so this is saying for every epsilon bigger than 0, and for every possible threshold, you can find something bigger than that threshold for which A sub n minus L is less than epsilon. Which is definitely not the same as convergence, right? Let's prove it's the same as being a subsequential limit. So, I want to prove if A sub n is a subsequence and L is a number, then L is a subsequential limit of A sub n if and only if for every epsilon bigger than 0 and every m in n there exists some little n bigger than big M such that absolute value of A sub n minus L is less than epsilon. Fair enough. So it's an if and only if. Let's prove both directions. Let A sub n be a sequence and L be a number. Declare your variables. That's important. Let's prove the forward direction. Let's assume that L is a subsequential limit of A sub n. So what does it mean to be a subsequential limit? That means there exists a subsequence which converges to L. So there exists some subsequence, let's give it a name, A sub n sub k, such that A sub n sub k converges to L. Now I've expanded out the definition of subsequential limit. So I've explained what my assumption says. Let's try to prove this statement. So let's consider any epsilon bigger than 0. Let's consider any big M. We need to find some little n bigger than big M. Because I need to, it's an existential claim. I get to choose what little n is. But it needs to satisfy absolute value of A sub n minus L is less than epsilon. So let's kind of get the idea of how to do that. That A sub n sub k converges to L, right? So can I find values of k for which A sub n sub k minus L is less than this small number epsilon? Yeah, I can, right? Just as long as little k is big enough, I'm good to go. So let's write that down. Since A sub n sub k converges to L, there exists some big N such that for all little k bigger than this threshold big N, absolute value of A sub n sub k minus L is less than epsilon. Well, that's good. This is like exactly that conclusion. So that n sub k looks an awful lot like what we need. But it's not quite everything we need, right? We also need n sub k to be bigger than big M. Well, how can we get n sub k to be bigger than big M? By taking little k to be like really big, can we eventually get n sub k to be bigger than big M? Yeah, right? It's a strictly increasing it's n sub k is a strictly increasing sequence. Let's use that claim. So here, I'll even give you the choice of big N prime that I'll use. Let's let big N prime be the max between M and N. Let's take any little k that's bigger than big N prime. I'll take little n to be exactly that n sub k. So here's the choice of little n, which I think should walk. So according to claim 2.5.3, the claim that's on the previous page, let's see what we can say. N by its definition is equal to n sub k. How does n sub k compare with just k?
Greater than or equal to.
Greater than or equal to. How does k compare with big N prime?
Strictly greater than.
It's strictly greater than. How does big N prime compare with big M? Greater than or equal to, because it's the max. So, by transitivity, we conclude little n is strictly bigger than big M. Hey, nice. That's one of the things we need little n to satisfy. Let's try to get this conclusion now. So, on the other hand, well, pretend you don't see that. How does k compare with big N prime?
Greater than.
It's strictly greater than. By assumption, how does big N prime compare with big N?
Greater than or equal to.
Greater than or equal to. So that means little k is strictly bigger than big N. So we can appeal to this line. For every little k that's bigger than big N, a sub n sub k minus a is less than epsilon. So we can conclude a sub n minus L. That's the same as a sub n sub k minus L. What's that less than? Epsilon. And so now, I mean, here's a concluding sentence. For every epsilon bigger than 0 and every choice of big M, we found a little n bigger than big M, satisfying that absolute value of a sub n minus L is less than epsilon. And let's just try to read through the proof really quickly and see if just logically we've done that. Did we consider any epsilon bigger than 0? Did we consider any choice of big M? Did we find a choice of little n? Was that choice of little n bigger than big N? Nope, was little n bigger than big M? Yeah, good. Was absolute value of a sub n minus L less than epsilon? Cool. That completes the proof of that half of the theorem. Let's prove the other half. Well, I guess maybe before I do that, do people have any questions they want to ask? Okay. So let's go the other direction. Let's prove that if this condition is true, then L is a subsequential limit. That's maybe the more interesting direction anyway. So let's assume that for every epsilon bigger than 0 and every big M, there's some little n, which I'll write as little n, which depends on epsilon and big M. So Ln is like a function such that little n is bigger than big M, and absolute value of a sub n minus L is less than epsilon. So all I've done is I've included in my notation the fact that the choice of little n depends on big M and depends on epsilon. Everyone feel okay about that? That'll actually be kind of an important idea in a moment. So here's what I'll do. I'll construct a strictly increasing sequence of natural numbers, n1 strictly less than n2 strictly less than n3, and so on, so that for every natural number k, a sub n sub k minus L is less than 1 over k. Do you think that if you knew this, you could prove that a sub n sub k converges to L? I see some like general head nodding. And maybe I'll give you a choice. I can talk through the proof, or I can like pause for a few minutes and then you compose the proof. You want me to just keep talking? Okay, I keep talking. Let's do this. So it's going to be a straight up, honest to God, epsilon n proof. So let's consider any epsilon bigger than 0. Let's let big N be equal to something that we get to choose. Let's let little n be bigger than big N. Then a sub n sub k minus L, we want that to be small. I need to somehow get that to be less than epsilon. But what do I know about a sub n sub k minus L?
It's less than 1 over k.
Less than 1 over k. And I know that right now because I said that I'll eventually justify it. K is the independent variable, not n. Okay. What can we do next? What can you tell me about 1 over k? Maybe using this line.
It's less than 1 over big N.
Less than 1 over big N. Do you think you could set that equal to epsilon and solve for big N? Do you already know what big N you'll get? I mean, if not, like, you have mergings. I think the argument will fit in the merging. Solve that for big N, you get. Yeah, n equal to 1 over the small parameter epsilon. So it's a big N be 1 over epsilon. If big N is equal to 1 over epsilon, then what can you tell me about 1 over big N?
It's equal to epsilon.
It's equal to epsilon. Does that complete the argument that a sub n sub k converges to L? Awesome. So let's see what that means. That means that if I can actually construct this strictly increasing sequence of natural numbers, then a sub n sub k, that subsequence, will converge to L. I just need to explain why that strictly increasing sequence of natural numbers should exist. And I will do so using recursion. And I'll take advantage of the fact that I have this formula for n dependent on epsilon and big M. So here's how I'll build it. I'll set n sub 1 to be n of 1, comma 1. So if you like, this is epsilon equal to 1, big M equal to 1. I'll set n sub k plus 1 to be little n of 1 over k plus 1, comma n sub k. So here my epsilon is 1 over k plus 1, and my big M is n sub k. So I need to show, one, that this is strictly increasing. Let's do that. Let's show that n sub k plus 1 is strictly bigger than n sub k. Let's start with this. N sub k plus 1 is equal to n of n sub k, 1 over k plus 1, comma, n sub k. Hell, I don't have a highlighter, but that's the closest I can come to highlighting. So what can you tell me about that quantity, n sub k plus 1? What are the things that I know about little n of m comma epsilon? Well, I know that it's bigger than big M, right? What is big M right here?
That's okay.
N sub k. So n sub k plus 1 is equal to n of 1 over k plus 1, comma, n sub k. Now, n of 1 over k plus 1, comma, n sub k is bigger than n sub k epsilon comma m. Does that prove that the sequence is strictly increasing? It does, and it was basically by its very definition, so it was an almost contentless proof. Let's prove next the other thing that we need. Let's prove that for every natural number k, a sub n sub k minus L is less than 1 over k. And this will look like an inductive proof, but it's really just like there are two cases in the definition. The case that k equals 1 and the case that k is bigger than 1. So tell me, when k is equal to 1, n sub k is equal to n sub 1 is equal to n of 1 comma 1. So this is epsilon equal to 1, m equal to 1. So let's see, by the definition of n of m comma n of epsilon comma m, what can you conclude? Well, let's go back and see the assumption, see what we have. We know that little n is bigger than big M. That doesn't seem useful right now. We also know that a sub n minus L is less than epsilon. So, what can I conclude when epsilon is equal to 1? Which is exactly what we need. So let's see, by the very definition of n of epsilon comma m, absolute value of a sub n of 1 comma 1 minus L is less than 1, which is what we needed in the case k equals 1. Let's do the rest, and maybe I'll speed up a little bit. Let's see, for every number k that's bigger than 1, I can write k as k minus 1 plus 1, and that seems like a silly thing to do, but it's just so I can unlock this. So let's see, so that means n sub k is the same thing as n sub k minus 1 plus 1 is, by the variable occurrence relation we used, n of epsilon equal to 1 over k minus 1 plus 1, comma, n sub k minus 1. I may have screwed up the order, I forget. So this is where epsilon is 1 over k minus 1 plus 1, which, let's stop kidding ourselves, that's the same as 1 over k. And m is n sub k minus 1. So let's see, by the definition of n of epsilon comma big M, we conclude what can we conclude about a sub n sub k minus L? Less than 1 over k. Nice. So let's see, this a sub n sub k that we constructed, is it actually an honest to God subsequence? Was n sub k strictly increasing? Yeah, we checked that in on the previous page. did we prove that the absolute value of a sub n sub k minus L is less than 1 over k? So a sub n sub k converges to L. Hey, nice, that means L is actually a subsequential limit. Cool. So I think I'm about 30 seconds over, but maybe well, the homework appears next, so I'm actually on schedule for where I want to be. Let me state the Bolzano Weierstrass theorem, which appears right here. I need to show that if n sub k is bounded, so the Bolzano Weierstrass theorem says that if you start with any bounded sequence, then that bounded sequence has a convergent subsequence. So the thing we saw from -1 to the n is actually what just happens all the time. You can always find convergent subsequences. Cool. And maybe I'll say that during the next lecture there appears a possibility for the final project, which is another proof of Bolzano Weierstrass, as well as an extra credit problem, which is another proof of Bolzano Weierstrass.
Courses here that already satisfied that BEE, and that BEE turned into a test, the validated by educational experience.
Okay, so
credit for courses.
ostensibly you can say that you already have credit for that exam as long as you get another exam or something.
Yeah.
Okay. Yeah, then, I mean, I think that, oh shit.